So therefore this summation k runs from 1 to n variation of the function f over the interval ck dk pk is always less than epsilon by 2 because the function f is absolutely continuous. Now let's take the supremum over all the partitions pk of the interval ck tk by taking supremum over the partitions pk of ck dk. This star gives, let's name it star gives a summation k runs from 1 to n, total variation of the function f over the interval ck dk is less or equal to epsilon by 2, and that's strictly less than epsilon. Okay, actually we need to show that the total variation function is is absolutely continuous. Also let's name it a double star. Also we have as in the proof of the previous result, we have this the total variation over the interval ck dk, total variation of f over the interval ck dk, it's equal to the total variation. You can easily verify it. It is equal to the total variation of f over the interval a to dk minus a to ck over the interval a to dk minus total variation of f over the interval a to ck over the interval a to ck. So this is already explained in previous theorem. So name this as triple star. Now let's add this k runs from 1 to n. We get therefore if this summation k runs from 1 to n dk minus ck is less than delta, then the summation k runs from 1 to n f of dk, not f of dk, it's total variation of f over the interval a to dk minus total variation of f over the interval a to ck. This sum, and this is equal to the summation k runs from 1 to n. You don't need to take the mod. Now we write here total variation of the function f over the interval ck dk. Okay, this is by triple star, you can see, and this one it's less than epsilon. It's less than epsilon by double star. Okay, it's less than epsilon by double star. So therefore that means this total variation function is absolutely continuous, because whenever this collection of bounded open intervals satisfying this property, that means the sum of the lengths of these intervals is less than delta, then the variation with respect over these intervals of the total variation function is less than epsilon, because this means the total variation at dk minus total variation at ck, that t of dk minus t of ck, and you are taking the sum k runs from 1 to n, summation k runs from 1 to n, mod of t of dk minus t of ck is less than epsilon, which means that total variation function t of x is absolutely continuous. So thus the total variation function tv f a to x, which is also denoted by notation t of x, is absolutely continuous, absolutely continuous. So therefore both tv f over a to x minus f of x and f of x are absolutely continuous, because fx is given to be absolutely continuous, and total variation you have proved this is absolutely continuous, therefore difference is absolutely continuous, and this fx is also absolutely continuous. So both the functions are absolutely continuous, and this fx is actually the difference of these two functions. It's equal to the total variation f over the interval a to x minus f of x plus f of x. So it's the difference of two absolutely continuous functions. So that proves the theorem completely. Next, we will discuss certain properties of monotone functions. We'll discuss certain properties of monotone functions. So that's very important. Yes, in fact, we will see that every monotone function is differentiable almost everywhere. That's very important result, and that result is proved by Lebesgue. So before proving that result, we first check certain properties of monotone function, and then after that we will discuss the Vitali cover. Then we will prove the Vitali covering lemma, and by that, with the help of this Vitali covering lemma, we will show that every monotone function is differentiable almost everywhere. Okay, so let's first check the certain properties of monotone functions. Properties of monotone functions. So a function is said to be monotone if it is either monotonic increasing or decreasing. A function f from R to R is called a monotone function. Is called a monotone function if it is either increasing or decreasing. Okay, so let's take some examples. Say f of x equal to x square, x belongs to R, is increasing if it's a monotone function. And second example, let's take this one. F of x equal to say e power minus x. You can say it's monotonic decreasing. So this one is increasing function, therefore it's a monotone map, and this one is decreasing. Okay, so both the functions are monotone functions. These are the examples of monotone functions. And one more example, that's the greatest integer function, or you can say it's a step function. Greatest integer. x belongs to R. This function is also monotonic increasing, and this is differentiable almost everywhere. You can see it's differentiable at every point except at integers, and the set of the integers is a countable set. Therefore, it's a null set. So that means this f dash x exists almost everywhere. F dash x does not exist on set of on set of integers, and we know that the set of integers has the big major 0. So therefore f dash x exists almost everywhere. That means f here, this f, it's differentiable almost everywhere. In these two examples, first and second, this f is differentiable throughout, but in the third example f is differentiable almost everywhere. And we will see in general every monotone function is differentiable almost everywhere. Okay, let's prove first property of monotone function. We will show that if the function is monotone, then f is continuous at every point except at countably many points. That means it's also continuous almost everywhere then, because it's continuous continuous on whole set except possibly at countably many points. But we know that the countable set has limit major 0, so that means it's continuous almost everywhere. But it is stronger than the differentiable, because the monotone functions are differentiable almost everywhere. It does not mean that the set where the function is not differentiable is countable. It may be uncountable set. But for a continuous function, the set where the monotone function is not continuous is always countable. That's this theorem. Okay, let f be a monotone function. Let f be a monotone function. Let f be a monotone function on the open interval. On the open interval a b, it may be unbounded. A and b may be infinities. Then f is continuous. So this ab may be whole real line. Okay. Then this f is continuous. F is continuous. F is continuous except possibly except possibly at a countable number of points, at a countable number of points. So since f is monotone, therefore it's either increasing or decreasing. First we assume that f is increasing. F is an increasing function. Also assume that this AB is bounded open interval. Also assume that AB is a bounded open interval. Okay, we assume that this AB is bounded open interval. In case it's not bounded, then we know that every open set, so this is always an open set. Every open set can be written as a union of countable union of bounded open interval. So for if this f is for if this interval is not bounded, for if AB is not bounded, then following cases arise. Then following cases arises. Case 1, a is say minus infinity. Then this a to b, which is equal to minus infinity to b, it can be written as union n runs from 1 to infinity minus n to b. So this is it can be written as and they are all bounded because and b is finite here, and this b, it is finite. So in that case this unbounded open interval can be written as the countable union of bounded open intervals, and it is an increasing sequence because for n equal to 1 it is minus 1 to b, for n equal to 2 it is minus 2 to b. So that sequence of bounded open intervals is increasing sequence. So that means in case this interval is not bounded, then I can express this interval as an increasing sequence of bounded open intervals. Case second. So actually what I have done earlier, also assume that this interval can be taken as bounded open interval. If it's not bounded, then I can write it as the countable union of bounded open intervals. Now I prove the result for bounded open. Suppose the result is true for bounded open intervals. Say the function is continuous on bounded open interval. It's monotone on bounded open interval. Then suppose result is true, that means it has only countably many discontinuities on each bounded open interval. Say first interval is minus 1 to b. In this interval the function has only countably many discontinuities. In the second interval minus 2 to b, it has again countably many discontinuities. In each interval it has only countably many discontinuities. And let's take the union of all such discontinuities. That's again countable, because we know that the countable union of countable sets is again a countable set. So that's why it is sufficient to prove the result for bounded open interval. If it is true for bounded open interval, then it's true for any open interval, whether it is bounded or unbounded. So it is sufficient to check that this every open interval can be written as the countable union of bounded open intervals, and that union is also increasing union. Case second. If suppose a is finite. Here this erase it here. Case second, if here minus infinity less than b less than infinity. Case second, if this a is finite, case second, minus infinity less than a less than infinity, and b is suppose it's equal to infinity, then in that case I can write this ab as ab, which is equal to a to infinity, that can be written as union and runs from 1 to infinity a to n. Again it can be written as countable union of bounded open intervals, because each interval is now bounded, as a is finite, n is also finite. And the last case in which both are infinities. Case third. A is minus infinity, b is infinity. Then what can we do in that case? Then a to b, which is equal to minus infinity to plus infinity, that can be written as union n runs from 1 to infinity minus n to plus n. So thus again it can be written as the countable union of bounded open intervals. Therefore we can assume that our interval a to b is bounded open interval. So we prove the result for bounded open interval. If it is true for bounded open interval, that means if the function has only countably many discontinuities in bounded open interval, then it has countably many discontinuities in every interval, every open interval. because every open interval can be written as countable union of bounded open intervals, and each bounded open interval the function has only countably many discontinuities. It is a B here. Okay, so that's every interval, whether bounded or unbounded, can be expressed as a union of can be expressed as the union of increasing sequence of bounded open interval, increasing sequence of bounded open interval, such that the closure of each bound open interval is contained in such that the closure of each bounded open interval is contained in this open interval A, B, which is unbounded. Okay, you can see what's the closure of minus n to plus n. It's closed interval minus n to plus, that's contained here because it is a whole real line. So that's every interval can be written as the countable union of ascending sequence or increasing sequence of bounded open intervals, such that the closure of each bounded open interval is contained in this interval A, B, which is unbounded. And then we take the union of discontinuities of each bounded open interval. Okay. So let's finally what we do, we take the union. Suppose we have an interval minus 1 to plus 1, we check the discontinuities over that interval minus 1 to plus 1, they are countable. Then we take the interval minus 2 to plus 2, again find these points of discontinuities of the function f, and so on. We'll do it for each bounded open interval, and then each such set is countable because the points of discontinuities is countable, and then we take the union of all discontinuities, all countable sets, and it is a countable union of countable sets actually, because we have only countably many intervals, and each interval contains only countably many discontinuities, and that means that's why we are taking the countable union of countable sets, which is again a countable set. So let's define the first left hand and the right hand limit at any point of the interval, bounded open interval. This AB is now bounded open interval. Okay, let x naught belongs to the bounded open interval A, B. It's any point of it. Then at this point we check whether when the function is continuous and when it's discontinuous. But since the function is monotonic increasing, therefore both the left hand and the right hand limit exist at this point x naught. Since the function f is increasing, is increasing, therefore both left hand limit and the right hand limit of f at x naught exist, and they are equal to what's left hand limit, which is equal to limit x approach to x naught from the left, and you can see it here. This is the interval, say a to b, where the function is defined, and this is the point x naught, and point is here, x is approaching to x naught from the left. Okay, and since the function is monotonically increasing, for each such point f of x is less than f of x naught. So it means that this limit is actually the supremum of this set. It's a supremum of f of x, such that obviously this a is less than x, a is less than x naught. Because it's monotonic increasing, it increases the value of the function f of x will increase to f of x naught, provided that the function is continuous at x naught, but in general it's equal to the supremum. Okay, it's equal to the supremum of f of x, where x varies over this interval a less than x naught. And similarly you can see the right hand limit, for right hand limit, suppose this is a point y which is approaching to x naught from the right, and here x is approaching to x naught from the left. So and this right hand limit f of x naught plus, what's f of x naught plus? It is the limit x approaches to x naught plus f of x, or you can say, I will write here y, rather than x I will write here y. Okay, it's y approach to x naught f of y, and you can see that's equal to the infimum of f of y, such that this x naught less than y, and y is obviously less than b. You can see at this previous speech, y is less than b, x naught less than y, y less than b. And since function is monotonic increasing actually, so this y is it decreases to x naught. So that's why we are taking the infimum, because on this part it's decreasing actually. The values of f decreases actually. Function is monotonic increasing, but values of f are decreasing here. You can see you are approaching to x naught. The values of f are decreasing because y is also decreasing to x naught. So fy also decreases. So that's why it's infimum of f of y. So f of x naught plus is this. And also this is true, f of x naught plus is less or equal to f of x naught minus. It's always true for as f is monotonic increasing, not always true for monotonic increasing, as f is increasing. Because here y is greater than x naught, and for f of x naught minus, what's x? Here x is less than x naught. So that means for this set x is here, and for the other set the y is here. That means x is less than y always. So in other words, f of x is always less than f of y. So values in this set are always less or equal to the values in this set. So if I apply the limit, or if we take the supremum over this set, it will always less or equal to the infimum over this set. But supremum over this set is f of x naught minus, and the infimum over this set is f of x naught plus. So that's why f of x naught minus is always less or equal to f of x naught plus. Okay, this is true. And the function is continuous at x naught if the equality holds. Function f is continuous at x naught if f of x naught minus is equal to f of x naught plus, and is discontinuous at x naught if f of x naught minus is strictly less than f of x naught plus, if the left hand limit is not equal to the right hand limit. Okay, so this is the case. So thus when the function is not continuous at x naught, we can define, therefore if f is not continuous at x naught, we define jump interval. Okay, that's called a jump interval. We define jump interval that is denoted by g of x naught at this point by, we define this jump interval by g of x naught, it's equal to all points such that f of x naught minus is less than y, less than f of x naught plus. So whenever this function is discontinuous at x naught, we have this jump interval, and it's always contained in this jump interval is always contained in it's always contained in this closed interval. Closed interval. It's contained in f of a, f of b, as f is monotonic, it subset of this as this f is increasing. Okay, so you can see this is the bounded interval actually, and how many jump intervals are possible in this bounded interval? You can see it here. You have f of a, and you have here f of b, and j of x naught is subset of this interval. So it's like this. These are the intervals. So this is the interval around x naught actually. F of x naught lies between these 2 points. F of x naught minus and f of x naught plus. So this is here f of x naught minus, and this point is f of x naught plus, and f of x naught is in between somewhere. It is an interval around f of x naught, but this interval is bounded. So how many such intervals are possible in this interval? So suppose how many intervals are possible of length say greater than 1? Obviously finitely many, because the total length is finite. So suppose total length is 100. So how many intervals are possible of length greater than 1? So cannot be more than 100. So suppose its length is 1000. So how many intervals are possible of length greater than 1? Again, it cannot be more than 1000. So now again, how many intervals are possible of length greater than 1 by 2? That cannot be more than 2000 if the total length is 1000 suppose. Similarly, how many intervals are possible of length greater than 1 by 3? That cannot be more than 3000 if the length of the total interval is say 1000. So in general, if the total length is, suppose it's here f of b minus f of a, in that case f of b minus f of a is the length. So how many intervals are possible? Such jump intervals are possible of length greater than 1, cannot be more than this number. If I take its greatest integer part, okay, its integral part cannot be more than the integral part of this, because it may be some irrational or rational number, it may be fraction. but the number of intervals that's a positive integer, so that's why I'm talking about this integral part of this number. So similarly, how many intervals are possible? Such intervals are possible of length greater than 1 by 2, that's twice this, not more than twice this. So that's why I'm now I'll write this. For each jump interval is contained in each that I have already written, and I will also write it here. Each jump interval g of x naught for any point where function is discontinuous is contained in that interval f of a, f of b. Okay, and the collection of jump intervals is disjoint, and that's very important, and the collection of jump intervals is disjoint. That's an exercise for you. Okay, suppose we have 2 points of discontinuous. Let x1 that's an exercise for you. If you take 2 points, suppose x1 and x2 be points of discontinuities, be points of discontinuity of f, then both have jump intervals. The jump interval with respect to x1, j of x1 intersection j of x2 is the empty set that you verify. Okay, the collection of jump intervals is disjoint means that for any 2 points x1 and x2 where the function is discontinuous, for any 2 points x1 and x2 where this function f is discontinuous, then these 2 jump intervals g of x1 and g of x2, they are disjoint from each other. You verify this. Okay, so they are disjoint, so that's why they are only the length. Suppose that if the length of the jump interval is greater than 1, then such intervals cannot exceed the total length, cannot exceed the number of such intervals cannot exceed the total length, the integral part of the total length of this interval, that's f of b minus f of a. Okay, therefore for each natural number, therefore for each natural number, therefore for each natural number n, there are only finite number of jump intervals. There are only finite number of jump intervals of jump intervals of length greater than 1 by n, of length greater than 1 by n. So that means there are only finite points of discontinuity, because whenever there is a jump interval, there is point of discontinuity, and whenever there is point of discontinuity, there is a jump interval. So if there are only finitely many jump intervals of length greater than 1 over n, so that means there are only finitely many, for each natural number n, there are only finitely many point of discontinuity of the function f. So the situation is like this. You have interval p f a f b, and for length greater than 1, you have only finitely many points of discontinuity. Okay, you have only finitely many jump intervals of length greater than 1, only finite. Say maybe you have only say 2. Suppose we have a point x naught, suppose point of discontinuity, that's the jump interval, and suppose we have only 2 in that case of length, say of length say 1, greater than 1 over 1. And similarly, the jump interval of length greater than 1 over 2. Suppose we have two more points here, see, of length greater than 1 over 2. Say these are the intervals, suppose, of length greater than 1 over 2. Only 2 points. Only 2 jump intervals means only 2 points of discontinuity. And you vary and runs from 1 to infinity, so you will get, actually it is now countable union of finite sets, because at each stage you have finite set. That means you have finite set of points of discontinuity. But you are taking when you vary and runs from 1 to infinity, so that means you are taking the countable union of finite sets, which is again a countable set, and that set is a point of discontinuity of the function f. So does the set of points of does the set of points of discontinuity of f is the countable union. Okay, is the union of countable, or you can say union of countable is the union of a countable collection of a countable collection is the union of a countable collection. So you are taking the union of countable collection. Collection is countable, and each set in this collection is finite. Okay, you are taking this union of a countable collection of finite sets of. Why it's countable? Because it's for each n runs from 1 to infinity. It's a finite collection. It's the union of the countable collection of finite sets. Okay, it's finite sets, and therefore is countable. Therefore is countable. That proves the theorem completely. Now, next theorem, which is also very important, as you have seen in the course Topology 1, where you have seen that there does not exist a function f from R to R which is continuous at rationals and discontinuous at irrationals. This function does not exist. There is no such function from R to R which is continuous at rationals and discontinuous at irrationals. There is no such function f. There is no such function. Close it here. There is no such function f from R to R which is continuous on rationals and discontinuous on irrationals. Okay, actually it's the application of Baire category theorem. But what about the function? Does there exist a function which is continuous on irrationals and discontinuous on rationals? If I interchange these sets, as you have seen that there is no function which is continuous on rationals and discontinuous on irrationals. But my question is that does there exist a function from R to R which is continuous on irrationals but discontinuous on rationals? The answer is yes, and in the next theorem we will prove more general part, actually more general than this in the next theorem. So what's the statement of that theorem? From that theorem you will get the particular case of function from R to R which is continuous on irrationals and discontinuous on rationals. let C be a countable set. Let C be a countable set. Let C be any countable set, countable subset. You can take countable subset of the open interval. It may be bounded or unbounded, of the open interval AB. Then there is an increasing function. Then there is an increasing function f from AB to R. For any countable subset C of AB, we can find an increasing function from AB to R such that that's continuous. That is continuous. That's continuous on AB minus C. That's continuous on that's continuous only. That's continuous only on AB minus C. That means that's discontinuous on C and the continuous on its complement. Okay, so since this C is countable, so we can take C as Q, the set of rational numbers. So for the set of rational numbers, I can always find a function from R to R which is continuous on R minus Q. That means which is continuous on irrationals but discontinuous on C minus Q, the set of rational. That's a particular case actually. And that function is not only continuous, that's also an increasing function. Right? Which is more stronger than that the continuous. It's increasing as well as continuous on irrationals but discontinuous on rationals. The proof if C is finite, then it's trivial. Then we don't need to prove anything in that case. If C is finite, say C is equal to some finite set, say x0, x1, so on up to xn, subset of AB. So in this finite set is always, it's a discrete set actually. Every finite set is a discrete set. It's a subset of AB, but at the same time it is also discrete. So these are the points. This is say x0, this is say x1, and so on. This is here now xn minus 1, and suppose that's the nth point xn. Now I want to define a function on AB which is precisely continuous on whole AB except on those points, and that function should be also monotonic increasing. How do I define that function? That's very important. Let's define the function. Okay, let's define this function. Define function. You can see it's very simple. It's not difficult. Define a function f by, say let's take this as f of x is equal to 0 if a less or equal to x and less than x naught, suppose, and it's equal to 1. It's like step function. If x naught less or equal to x, less than x1, and so on. You define f of x equal to n if xn minus 1 less or equal to x, less than xn, and then after that you will define it n plus 1 for xn less or equal to x and less than b. Let's take this function. This function is continuous on the interval a to x naught. Okay, but it's not continuous at x naught because the value of the function at x naught is 1, but its limit from the left hand side is 0. So it's not continuous at x naught, and it's continuous in the open interval x naught to x1 as it's constant on that part, so it is continuous, but not continuous at x1 because the limiting value of the function at x1 is 1, but the value of the function, you can see the next point, it's equal to 2 at x1. Value of the function at x1 is 2. And similarly, you can see it's not continuous at xn minus 1, because at xn minus 1 the value of the function is n, but the limiting value is n minus 1. So that's very simple. It's continuous on each open interval here, but not continuous at those points x0, x1, so on up to xn. That's our set C. And that function is also monotonic increasing, because when you are increasing the points, the value of the function is also increasing. It is first 0, then 1, then 2, and so on and so forth. So this f is monotonic increasing, and it's continuous on a, b minus c, except those points. So in that case, it's trivial if the set is finite. Actually, in that case, set's actually discrete. You can see. So there is a distance. There is a gap between the points. You can see that gap actually. So next, if the set C is not finite, if C is not finite, but it's countable, okay, that means it's countably infinite. So again, in this case, we have two cases. If the set is discrete, then it's trivial. Again, you can define function like that. On whole real line, say C is subset of the whole real line, you can take it as discrete subset, which is also countable. Say set of natural numbers you can take. Then you define this step function phi of x is equal to greatest integer of x, and that discrete step function is continuous on whole real line or except this integer set, which is our C. But in general, it may not be like that. It may not be like this type of discrete type of set. It may be set of rational numbers, which is not discrete. So we have to prove it in general. C is any countably infinite subset. It may be discrete or it may not be discrete. So for this, if C is countably infinite, we define a function. We define function. Define a function f, define a function f from AB, it's open interval AB to R by f of x equal to C. This definition, it's very interesting. This construction is very interesting. It is that those natural numbers. So C, let me write this C. It is those natural numbers such that Qn is less or equal to x. Okay, 1 by 2 power. And what's this Qn actually? C is countable infinite. So where this C, it's a set. This set Q1, Q2, it's countably infinite, Qn, then so on. This is this set. We define function like this. Now we find those Qn's for a particular x which lies in the interval AB. Then we find those Qn's which are less or equal to x. Then you check the subscripts of those Qn's, and you will take this series. Suppose for a particular point, say 5. Suppose you take 5 of 5, and you find Qn such that Qn less or equal to 5. Suppose Q1 is less or equal to 5. Say Q6 is less or equal to 5. Q7 is less or equal to 5. Then the values of n's are say 1, 3, 5, 7. So then in that case, the value of the function is 1 by 2 power 1 plus 1 by 2 power 3 plus 1 by 2 power 7. So this series depends upon the subscript of that Q's, which is the countable set. C is a countable set, countably infinite set. So here I will explain it again. We have an interval AB, and we have defined a function on that on any point x of this set. Then we have a countable subset of AB. Say we have here Q1, then here suppose we have here Q5, we have here suppose say Qn is here, suppose, then we have here say Q2, suppose. It's not in the proper order. It's a countable set. It's suppose now here say it's equal to say Q3, say, then suppose it's here q10 here, suppose it's here q8, so it may be in any order, and you find those q's which are less or equal to x. Say suppose here it's q1, here is q1, q5, q, say let me write q9, suppose q9. Okay, then at this point what's the value of x? It's equal to 1 by 2 power 1 plus 1 by 2 power 5 plus 1 by 2 power 9. 1 by 2 power the subscript of that q, which is less or equal to x1, then plus 1 by 2 power the subscript of the another q, which is less or equal to. If there is only one q which is less or equal to x, then this sum contains only one term. If there are two q's, then this sum will contain two terms. If there are three, then this will contain three terms. If there are infinitely many terms, then this is an infinite series. But after that, this series is a geometric series with common ratio 1 by 2. So it will never diverge. It will always converge. That's why therefore this function is properly defined actually. So now since a geometric series since this is a geometric series actually, since so if it will contain each term, then it is a geometric series with common ratio 1 by 2, therefore it is convergent. But if it will not contain all the terms, it is not a geometric series in that case, but the sum is still finite, because the if it will not contain all the terms, then we will add those terms, then this sum will be less than that sum, because that sum contains all the terms, and that sum is always finite. Since a geometric series with common ratio less than 1, its ratio is 1 by 2, with common ratio less than 1 converges with common ratio less than 1 converges. So therefore f is properly defined. Therefore f is properly defined. Therefore f is properly defined. Now we will see that this function is monotonic increasing. So let now we first show that this f is increasing. This f is increasing. So let u comma v belong to the open interval a b such that u is less than v. We need to show that f of u is less or equal to f of v. Now look at the definition of the function. It's trivial. It's less or equal to. Look at the definition of the function. We have to find f of x. So this is the interval a b, and these are the points u is less than v, and you want to find those q's which are less or equal to v and those q's which are less or equal to u. Obviously any q which is less or equal to u is also less or equal to v, but any q which is less or equal to v may not be less or equal to u. So that means the number of q's which are less or equal to u is bigger than the number of the q's which are less or equal to u. So that means the series corresponding to those q's which are less or equal to u is obviously greater or equal to the series which corresponds to this, which correspond to the q's which are less or equal to u. It may be equal. There may the number of the q's may be equal. In fact, the set of the q's may be equal, but in that case there is no any q lying between u and v. Then all the q's are less or equal to u, and all the q's are any q which is less or equal to v is actually a q less or equal to u if there is no any q lying between u and v. In that case the value of f of u and the value of f of v are same. But in case there are q's lies between u and v also, then that term in the sum corresponding to the q's lying between u and v cannot be in that sum. cannot be in the sum for the function for the value f of u. So in general we have f of v is greater or equal to f of u. So then you can see this f of v minus f of u, it's equal to summation of the n's such that summation of the n's such that those q's they lie between, because it's f of v minus f of u. So f of v means less or equal to v, but at the same time less or equal to u of you are subtracting less or equal to u. So that means this is u strictly less than qn and less or equal to v. So the q's which remain in this portion, only the sum with respect to those q's will remain. Those terms which are less or equal to v, those q's which are less or equal to v, they will cancel because it's f of v minus f of u. These terms, the sum with respect to the q's which are less or equal to u, that sum lie in both the values f of v as well as in f of u, but you are taking the subtraction of f of v and f of u. So these terms will cancel in the sum, and in the sum there remain only these terms, 1 by 2 power n, which is always greater or equal to 0. It's equal to 0 in case there is no any q in between this u and v. So that means f of u is less or equal to f of v. So therefore f is increasing. Therefore f is increasing. Next we will show that f is not continuous at any point in C. Next, second property. F is if x naught belongs to C, then f is not continuous at x naught. Let's verify this one. Now since this x naught belongs to C is a countable set, it's q1 q2 q1, this means that x naught belongs to say qk for some k, because it is in the set C. So let's take any point, let x be less than x naught. Then I want to find the difference f of x naught minus f of x. I will see this difference is greater than some positive number, and this can be seen from this here it's a point A, this is the point B, and this x naught is here somewhere and x is here, and you want to find f of x naught minus f of x. This x naught is equal to qk. Okay, so qk is already there. So what's the difference? This it's greater or equal to 1 by 2 power k, because at least this qk remain in the sum. Suppose there is no any q lying between x and x naught, then you are taking the subtraction f of x naught minus f of x naught minus f of x. That means you are subtracting the series which corresponding to those q's from the series corresponding to the q's which are less or equal to x naught. So obviously obviously you can see it's already done in the case of when we have proved that f is monotonic increasing. You can say it's equal to directly you can say it's equal to the summation 1 by 2 power n, those n is such that x less than qn and less or equal to x naught is qk. So at least in that interval one qn is there, that's qk is equal to x naught. So that's why this series contains at least one term, that's 1 by 2 power k. So it may contain other terms, but at least it contains that positive term 1 by 2 power k. So therefore it's equal to greater or equal to 1 by 2 power k. And it's true for any x which is less than x. So that means whenever x is approaching to x naught, but f of x may not approach to f of x naught, because the difference is always greater or equal to 1 by 2 power k. So which means this f is not continuous at x naught. F is not continuous at x naught. Next, we verified that f is continuous. F is continuous on the interval a, b minus c. It's continuous at every point of the interval other than this point c. At c you have shown that it is discontinuous at each point of c, but on the rest of points you will see that it is discontinuous. You verify this yourself. Okay, this is very simple, and you can see the page number 109 of H.L. Royden. Okay, you can see this book, H.L. Royden, at page number 109. Okay, now suppose now we take its application part. Suppose this interval AB is equal to whole real line R, and this C is equal to set of rational numbers. Then between any two real numbers there is a rational number. So then in that case this function f of x, which is equal to series q, which is series over n, sorry, it is series over n, such that q n less or equal to x 1 by 2 power n. This is increasing, this is strictly increasing, rather is strictly increasing. Why it is strictly increasing? And you can see the reason here. It's strictly increasing because of this, where we have proved that it is increasing. Actually it follows from this. Then in that case it is not greater, it is greater than 0 in that case, because we have to find the rational number between u and v, and there are infinitely many rationals between any two numbers. So this series is not like empty series, it contains certain terms, so that means this sum is a positive number, so that's why this function is strictly increasing in that case. Okay, so that means there is a function from R to R. So there is a function from R to R. So therefore there is a function from R to R. There is a function f from R to R which is strictly increasing. Second, continuous on irrationals. And third, discontinuous on rationals. Discontinuous on rational means it is discontinuous at each rational point. You can say discontinuous at each rational point. You can write it like this: discontinuous at each rational point. Discontinuous at each rational point. Okay, now in the next theorem we will define Vitali cover, then we will prove Vitali covering lemma. After that we will see that the application of Vitali covering lemma is that every monotone function is differentiable almost everywhere. Thank you.